Okay, third time's the charm. Let's work on WA6. So we're going to start with the interface that I included with the assignment. And remember, what we're building here is just a generic graph API, a graph representation class that we're going to use going forward to do some other interesting things. So we'll start out with our guards. So we don't want the preprocessor to include this multiple times if we happen to accidentally do that. And let's just kind of look at what we have here. I'm going to use using namespace here, even though in general, in production code you probably wouldn't, just to clean up the code a little bit. So we have a convenience type here, which is going to be our adjacency list. So this is a map that has key value pairs, which are integer, that's going to be the vertex number, and a set of integers, which are the vertices adjacent to the key. And we're going to call that a map T, that type of map T. So that's our adjacency list. This is the number of vertices. This is the number of edges. Meaningful names, right? And then a couple of constructors. Default constructor, we'll use that mostly for when we derive or inherit from this class. And read edge list from standard in. And then a couple of accessors. And then this is going to be the actual list of vertices. Because we'll need that sometimes when we kind of iterating through the vertices in the graph. And we want that to come out as a set because we want it to be an ordered list of vertices from the graph. And when we get to some of the algorithms, we'll see why that's important. So vertices adjacent to a vertex, and of course that will be important. We know that's important from the work or from the videos that we watched concerning the different graph representation types, right? Those are basically the operations that we expect our API to support. Now this graph API is loosely associated or loosely mapping the one that Robert Segwick uses in his data structures class from Princeton. He uses Java and has some slightly different representation methods, but the idea is the same. We're going to have a graph class which represents the graph, and then we're going to build client classes on top of that graph class to do various interesting things to the graphs. So this is overridable. And we'll see why that's important later, because regardless, or depending on whether or not we have a directed or undirected graph, we're going to want to do this slightly differently. So that's basically our interface, and I'm going to move that over here now so we have it for reference. And now we want to start implementing the interface. So the first thing we're going to do is include our graph class, and then let's see, well, let's just start. We'll just work our way from top to bottom. So we're first going to do our default constructor, and then we're going to do the one where we build the graph from an input stream, whether it's a file or standard in or whatever it is. And this file is going to look like this. We're assuming. Right, just an edge list. So as the edges come in, V and W, those represent a pair. And again, depending on what type of graph we're talking about, it's going to be an ordered or unordered pair. So we need a V and a W, and then while not f in end of file, we're going to read in V and W, and then we're going to add edge VW. That's good for now. We'll probably come back here. We need to augment this a little bit, but let's continue working our way down. So now we have an accessor which is going to return the number of vertices in our graph. Remember, we have to match the signature. And then we're going to return the number of edges in our graph. And then what? Then we want to return a set of vertices in the graph. And how are we going to do that? Well, we're going to create a set, verts, and we're going to loop over the key value pairs in our adjacency matrix, or our adjacency set, or adjacency tree, I guess, because we're using a red-black tree. Let's see, how do we want to do that exactly? Let's see, we want to loop over, right, key value pairs, so it's got to be our vertices. And then verts is a set, so we're going to insert basically all the keys from our dictionary or our map. And we're going to return that set. Okay, now we want to do this. We want to return the list of adjacent vertices to a particular vertex. And remember, the value part of the key value pair is that set of adjacent vertices. So we'll just return that set of vertices. What's next? Now our edge list, or add an edge rather. And we're going to take in a V and a W. Now here we make a decision. Is the base class going to assume that we have a directed or an undirected graph? I think in general we want to assume that the base class is an undirected graph, and we'll derive more specific versions from there. So when we send a pair, vertices V, we're going to insert W into V's adjacency list. And we're going to insert V into W's adjacency list. Okay, so now here we're returning num edges and num vertices, but right now they haven't been assigned. Where can we assign them? Well, once we've looped over our entire file, we know we have everything we need. We know the number of vertices is going to be the number of keys in our map. The number of edges is a little harder. We're going to ask the graph for the vertices, and then for each V in vertices, we're going to add the number of vertices that are adjacent to V. Right? So what vertices V, this key V, is going to return is our value. Our value is a set. We can take the size of the set, add that to num edges, and get the result. Now there's a little something wrong with that, but we'll come back to it. So let's see if what the compiler thinks about what we've done so far. Oh, doesn't like it. Looks like we haven't included the std files that we need to make the compiler happy. That's better. Bad spelling on my part. Number to C's, not ver to B's. That's better. So with the assignment, I also included an example usage. If we go to the bottom, you'll see this link here, and we have this main that we can grab. So we're going to call the constructor. Oops, the constructor is going to loop over the input file and build our graph. So once this is constructed, everything is in there that we need. So we can print out the number of vertices the graph thinks it has, the number of edges the graph thinks it has, and then we're going to print out the adjacency list, each vertex and the vertices that are adjacent to it. So let's see if that will compile. And it did. Now we need an input file. And we're going to use the graph, right? We're going to use the graph from the book that all the examples seem to build off of. And I also included that in the assignment. If you go down here, that's this guy. Now this set of vertices, this set of edges, rather, edge list, is a directed set of edges. In other words, you'll note duplicates. So there's a 1, 2, and a 2, 1 here, but that's fine because sets don't allow duplicates. You know, the sets will take care of that for us. We won't actually have duplicates. So now we can run main with an input file like this and say, let's see what we get out of the graph. So let's see how we did. So number of vertices 7, 1, 2, 3, 4, 5, 6, 7. Number of edges 24. That seems like a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's because we're double counting edges, right? So we counted this edge as adjacent to 1, and we counted this edge as adjacent to 2, but in an undirected graph they're the same edge. So we've got a slight problem, which we'll fix here. Right? So now we're going to count the edges, divide by 2, because remember, for an undirected graph, it's v times v minus 1 over 2. Remember, for a completely connected graph. So that divided by 2, that's this guy here. All right, let's recompile. Oops. Rerun. Everything looks right with the world. Okay.